Classical computer might be great at difficult tasks like sorting through a big database of a molecule, but it will struggle to solve more problems like simulating how the molecule behave. Today, we are going to discuss what is quantum computer. Today, for the most part, if scientists want to know how a molecule will behave, they have to synthesize it and experiment with it in the real world. If they want to know how a slight tweak would impact its behavior, they usually need to synthesize the new version and run the experiment all over again. This is an expensive, time-consuming process that impedes progress in fields as diverse as medicine and semiconductor design. A classical supercomputer might try to simulate molecular behavior with brute force, leveraging many processors to explore every possible way every part of the molecule might behave. But as it moves past the simplest, most straightforward molecules available, the supercomputer stalls. No computer has the working memory to handle all the possible permutation of molecular behavior using any known method. Quantum algorithms take a new approach to these sort of complex problems, creating multi-dimensional computational space. This turned out to be the much more efficient way of solving complex problems like chemical simulation. We don't have a good way to create these computational spaces with classical computers, which limits their usefulness without quantum computation. Industrial chemists are already exploring ways to integrate quantum methods into their work. This is just one example. Engineers, engineering firms, financial institutions, global shipping companies, among others, are exploring use cases where quantum computers could solve important problems in their field. An explosion of benefits from quantum research and development is taking shape on the horizon. As quantum hardware scales and quantum algorithms advance, any big important problem like molecular simulation should find solution. Now let's come to the topic: how do quantum computers actually work? An IBM computer processor is a wafer not much bigger than one found in a laptop, and a quantum hardware system is about the size of a car, made up mostly of cooling system to keep the superconducting processor at its ultra-cold operational temperature. Classical processor uses classical bits to perform its operation. A quantum computer uses qubits to run multidimensional quantum algorithm. Superconductor. Your desktop computer like use a fan to get cold enough to work. Our quantum processor need to be very cold, about 100th of the degree above absolute zero, to avoid decoherence or retain their quantum state. To achieve this, we use supercooled superfuel. At these ultra-low temperatures, certain materials exhibit an important quantum mechanical effect. Electrons move through them without resistance. This makes them superconductors. When electrons pass through superconductors, they match up, forming Cooper pairs. These pairs can carry charges. Across barriers or insulators through a process known as quantum tunneling. Two superconductors placed on either side of an insulator form a Josephson conjunction. The next is control. Our quantum computers use Josephson junction as the superconducting qubit. By firing microwave photon at these qubits, we can control their behavior and get them to hold, change, and read our individual unit of quantum information. Superposition. A qubit itself isn't very useful, but it can perform an important trick. Placing the quantum information it holds into a state of superposition, which represents a combination of all the possible configuration of the qubit. Groups of qubits in superposition can create complex, multidimensional computational spaces. Complex problems can be represented in new ways in these spaces. Thank you for watching today's video. That is what we have for this tech related video. Hope you find it very informational. Bye and stay tuned.